Murthy Ramesh is extremely known to India, as far as I understand, and it's very famous for many achievements. And this slide shows his research interest and achievements. I just want to make a comment to organizers that we can somehow downgrade his achievements in terms of citation and H factor. First of all, on a page which I got, they only mentioned 32,000, which is actually citations since 2016 by themselves, very impressive. But Professor Ramesh has almost 100,000 citations in Google, and H factor 144, much higher than mine. So anyway, I just because we're already late, I just want to pass to Professor Ramamurthy Ramesh for his presentation, which is has a title Observation of Room Temperature Polar Skyrmions.
Thank you, Professor Kivshar. Pleasure to meet you. I've read some of your papers, and hopefully there will be a crossing point. First, let me see if I can. Hey, Kamala, I have to share my screen. Professor Bharati.
Yeah, you're now back.
Yes, so Professor, now you can share.
Yep, got it.
Yes.
All right. Yep, thank you. Can you see my screen?
Yeah, yes.
All right, very good. Yeah, so thank you for letting me join this. This is a fantastic event that you guys have done. I have no idea how you're able to pull off 500 students, postdocs, faculty members amidst a blazing pandemic. You know, we are all sitting at home. You know, I was feeling goofy about wearing a jacket for the opening ceremony because we're just sitting at home. The one good thing that's happened is we still are doing science. And so it's been fun. What I thought I would do is I have a position which is between the physics department and the engineering school in material science and engineering. So a part of my work, I would say half my work, is looking at how do you take fundamental physics discoveries, materials physics discoveries, and translate them into real applications. Pretty much what Ashutosh was talking about 5-10 minutes ago. I wasn't planning to talk about that because I figured, okay, this will be more of a condensed matter physics talk. So in that work, what we are looking for is what happens beyond Moore's law. This is the whole underpinning for microelectronics. And the question is, things are getting smaller and smaller. It's getting more and more expensive to make electronic devices. What happens beyond Moore's law? And so we are deep into exploring the universe outside of the electron, which is the fundamental particle for all of the work on semiconductors. So the question is, can you use a different order parameter instead of the charge on the electron? What about the spin on the electron? What about order parameters like magnetism, like ferroelectricity? Can we start to think about applications like that? And that was the other talk that I kind of decided, okay, I will do more of a physics talk. Okay, what I wanted to tell you about today is some really fun stuff. And this is where, you could go to the lab, even amidst a pandemic, and you could have lot of fun doing some things which are completely unexpected. And that's part of I would say a big part of doing science is the fun of discovery. So the title is, of course, creating and manipulating spin and charge ordered textures in oxide superlattices. And the real title is, how do I look at polar skyrmions? For which you have to say, hey, what is a skyrmion? Before that, acknowledge all the people. The other part about doing science is that you get to interact with the world. Of course, my world is the world of condensed matter physics, material science. We work a lot with folks in Europe, quite a bit with folks within the US, the various groups across the country. We work quite a bit with folks in China. Many of my former students and postdocs are big professors now at Tsinghua and other universities. This fellow is a really smart fellow. He's in Zhejiang now, folks in Europe and stuff like that. And of course, like you all in India, we need funding from funding agencies. We've been fortunate to have the Department of Energy and the Army Research Office fund this work. Okay, what is it that we're talking about? If you look at materials like a ferromagnet, you could see that typically in a ferromagnet, you will form things called domain walls. Why? Because magnetostatics says, hey, look, the energy of the system is too high. And therefore, you say, how do I reduce the energy? If you form anti-parallel domains, for example, that's one way to do it. And the region between them, that blue surface, is basically a wall. It's a domain wall. It looks exactly like the apartment wall that you have in your house. Now, it turns out a few years ago, our colleagues in magnetism discovered that you can form some very exotic structures which are nothing like a magnetic domain wall. So some of them can look like rotating dipoles. They could look like vortices, like we heard in the introduction. They could also have anti-vortex-like structures. They're called skyrmions, and we'll talk about why they're called skyrmions in just a second. They could be the nail type, and you can see these are the spins on, let's say, a piece of a ferromagnet. The spins are pointing down at the core and pointing up outside. You could have a block type skyrmion where the spins are rotating this way, spiraling patterns. You could have something called a meron, which is a half skyrmion, or you could have an anti-skyrmion or an anti-meron. All kinds of, it looks like we have discovered a whole new taxonomy of quasi-particles in physics language. And these are quasi-particles because they actually behave like an entity. Okay. I want to take you through a little bit of the physics. Where does this come from? And then ask the question, how do I get a parallel universe? So if you look at a ferromagnet, for example, you will see that there is exchange interaction, which is such a fundamental aspect of a ferromagnet. And that's given by the Hamiltonian here, which is given by this. And this is a very important functional form, is S1.S2. And if we have a piece of iron and which ferromagnetic, S1.S2 is the lowest energy when the spins are aligned parallel. In an antiferromagnet like manganese, it would be the lowest energy if they're antiparallel. Now, in reality, when you write down the full free energy functional, you also have to include the cross product, S1 cross S2. In many systems, in 95% of the systems, that cross product term will drop out because of the symmetry of the crystal, crystal-like iron, for example, which has too high a symmetry, body-centered cubic. On the other hand, if you have an interface automatically breaks inversion symmetry. And therefore, you could have at the interface a very strong S1 cross S2. And it shows up with this vector called the Dzyaloshinskii-Moria vector. Igor Dzyaloshinskii back in the late 50s and Professor Moria at Bell Labs, they discovered this so-called antisymmetric coupling. An interface can create that. Spin-orbit coupling is a very important component of that. Professor Pert, who's a dear friend of mine, has a beautiful review article. You should read it. Okay. So if you now have a system where both of these are playing a role, then you can start to have these kinds of textures. The ratio between this D value, the so-called Dzyaloshinskii-Moria term, or the cross term, and the J value, which is the so-called dot product, determines the nature of the skyrmion. If D is very large, the skyrmion is very tightly wound, and if D is very small, it has a very large size. And therefore, you can start to define something called the skyrmion number, which is given by this cross product, M dot, the gradient of M cross Mx and My integrated over the whole surface. And that is called the skyrmion number, and it's like a quantum number for the system. Okay. This review article describes all of that. You can write down the free energy for this entire system. Of course, you have the first term, which is the standard exchange term, which is the symmetric exchange. The second term is a Dzyaloshinskii-Moria term, or the antisymmetric. You can see the cross product there. The third term is a Zeeman term. It's the forces observed on a magnetic dipole moment in a magnetic field, or demagnetizing in a more macroscopic sense. And the fourth term is a magnetic anisotropy term, which typically comes from magnetocrystalline anisotropy. Okay. Now, with all of this, you can then start to say what kind of textures. And in our magnetism community, starting around 2005, there's been a whole bunch of work. Now, Yoshi Tokura, a dear friend of mine at University of Tokyo, has been a pioneer in this field. And you will hear from Hide Hosono next from Tokyo Institute of Technology, spectacular work on transparent conductors. So Tokura has been doing quite a bit of work in this. This is now a whole field of spin textures. And the question is there an electric or a dipolar analog? And for a long time, people said, oh, that doesn't make sense. The dipole moment can change up and down, while the spin magnitude cannot really be changed. There is no magnetic monopole. There are electric monopoles. So people felt this wouldn't happen. Okay. Emerging of artificial heterostructures completely changed this. It actually started with theoretical work. Ab initio theory folks were saying, guys, if I took a very small piece of a ferroelectric and confined it, you would start to see some very exotic dipolar textures. And so about 6-7 years ago, maybe even longer, we started creating artificial superlattices. And what you see here is basically an atomic resolution image. Each one of these dots is a lead atom. The smaller dot is a titanium atom. Each one of these dots is a strontium atom, and these dots are titanium atoms. So we can use the power of heteroepitaxy, I'll get to that in the next slide, and start to create these artificial structures. I can put polar gradient, elastic gradients, dielectric gradient, gradient in the Landau potential. I can put gradients in octahedral tilts and rotations. It can get very exotic. And then I can go into the other fundamental degrees of freedom, the spin, the lattice, the orbital degrees of freedom, and start to play games with this. Therefore, epitaxy is a very important tool for us, people like myself. We use epitaxy as a powerful tool to create these model systems. I can engineer the ground state of the system by strain engineering. I can start to break symmetries. I can take a material which has a higher symmetry, and with epitaxy, I can break symmetry. I can design new states of matter at interfaces by interfacial engineering. I can create vertical nanocomposites, looks very much like a cigarette box with epitaxy as a driving force. I can stabilize metastable phases using epitaxy. Or I can do doping at very, very small scales by proximity effects. You know, I can have a semiconductor in contact with the ferroelectric, or I can confine things to very, very small dimensions. So the power of epitaxy in creating model systems has been a dramatic boon for all of us materials physicists. So this is what we did. And this is a textbook kind of a picture. What it is a superlattice of lead titanate, which is this layer, and strontium titanate. And the student who did the electron microscopy, this is an atomic resolution microscopy image. And these yellow arrows you see there are vector mapping of the displacement of the titanium ion with respect to the lead ion. And when we saw this picture, we said, oh my God, this is fantastic. And what we're looking at are vortex-like structures. One of them is rotating clockwise. The other one is rotating counterclockwise. And these are theoretical calculations, phase field calculations, which use this Hamiltonian, which has, of course, the Landau bulk energy, the gradient energy. The two terms that are very important is the elastic and the electrostatic energy. As you can see in the bottom picture, this is exactly this vortex array. But you could see that this is the color you see there is the curl of the displacement. And therefore, it's telling you that as you get closer and closer to the center of the vortex, the curl, which is del cross of the P being the order parameter, is getting stronger and stronger and stronger. Very much like a hurricane, okay? And as you go closer and closer, it starts to spin faster. Very much, except there it is the velocity vector. Here it is not the velocity vector, but it's really the dipole moment which is rotating. So when we saw this, we said, oh, this is really fantastic. How does one really understand the properties? As it turns out that this was completely unexpected. Nobody expected to form these kinds of vortices. our theory colleagues, this is phase field calculations, showed that indeed they do form. These are indeed the ground states. You can see one of these vortices rotating like so. This looks very symmetric. If you look at it from the top, it looks very much like a bunch of tubes. I'm going to show you images of these tubes in just a second. And you can look at the dipolar distribution. This looks something like this. These are the dipoles going in and out of them. And that's what this picture is showing. Okay, now with this theoretical background, we can go back and say, how do they really look like? And it turns out that if you do an electron microscope cross-section of the structure, that looks very much like what you see, except it's got a lot more richness to it. If you look at this, each one of these stripe-like things is one of these vortices. So that length scale is of the order of 5 nanometers. But that's not all that you see. If you look at it, there are these boundaries. It looks like there are defects in the structure. It looks like there are other defects, which if you blow it up, you can see very clearly. That looks like a phase boundary or an antiphase boundary. But if you look at it more carefully, you can see that these red circles are highlighting dislocations in them. And that's very interesting because a couple of years ago, Kasserlis and Thouless and Professor Haldane won the Nobel Prize for these new topological phase transitions. And what they were talking about is a topological phase transition, meaning that the transition, for example, in a 2D ferromagnet, the ground state is not an ordered state, because any kind of fluctuation can actually destabilize it. Instead, what happens is it forms a whole range of correlations, and one can think of the transition in these kinds of systems to be very different. They have exponential behavior near the phase transition. And Kasserlis and Thouless explained this. They got their inspiration for all of this from the metals literature in the 1930s, looking at Nabarro's work, Friedel's work on looking at how dislocation can mediate a melting process. And indeed, we see dislocations in them. And therefore, we're thinking, this system could behave very much like a Kasserlis-Thouless system, which was originally described for magnets and superconductors and so on. Okay, so in the next few minutes, I want to tell you a little bit about what can you do with these kinds of vortices. Before I do that, I want to give you some very simple physics background. So if you can visualize these things, these materials at high temperatures, they are in a paraelectric state. And so if you look at the free energy versus order parameter, that looks like a parabola, with the lowest energy being at 0 polarization. Of course, there is no polarization at high temperatures. On the other hand, if you go to very low temperatures, below the transition temperature, you will start to see this double well-like structure. Very classical Landau physics will explain this for you. Now, here's the interesting piece in the double well structure. If I looked at the second derivative of the free energy, which is really the permittivity of the material, right here, that derivative was negative. And therefore, the material is not stable in this state. Instead, it'll roll down to this point and this point, where the curvature of the free energy is positive and the material is stable. Okay, and so you could also explain it in terms of the electric field. So what you can say is that typically the negative permittivity state is not stable in the system. In just a couple of minutes, I'm going to show you, oh, by the way, that may not be true. All that this is saying is that for a global, the entire material, negative permittivity is not stable, because that will automatically lead to this thing rolling down the hill to go to this point, where it is positive permittivity. Now, when we started looking at this vortices, one of my colleagues at Cornell, David Mueller, bar none one of the best microscopists I've seen, what he has is an angstrom electron beam. It's a very coherent electron beam. When you shine it through these vortices, the beam will start to rotate. And you can actually change the angular momentum of the electron. And you can map it out as a function of spatial location. For example, the blue is rotating to the left, and the red is rotating to the right. And this length scale is 5 nanometers, about 12 to 14 unit cells of the material. And you can see that it basically maps out these vortices. One is a right rotating, the other one is a left rotating. It's very interesting that it rotates by h bar by 2. And nobody still knows whether that's a fundamental quantity, some kind of quantization, or it just happens to be. Okay. Now, what David Mueller and his student did, along with Saif Salahuddin, who is a wonderful colleague of mine here at Berkeley, very smart Bangladeshi origin physicist. He's in the electrical engineering department. So what we did was we took this electron beam. We could measure the torque on the beam, which is coming from the angular momentum. We could also measure the spatially resolved potential of this with the holographic type measurement, and you can convolute the two of them to map out the potential energy. And therefore, you could see that somewhere between these two, there is a maximum here in potential energy, another maximum here, and the minimum is here. Okay, and so you could envision that you have created a structure that looks exactly like this, but at the scale of one of these vortices, at the scale of a few nanometers. This length scale is of the order of 5 nanometers. Okay, and therefore, what this told us was that indeed, in these vortices, you have regions. If you can reconstruct the energy landscape looks like this right at the center of the vortex. And therefore, we have indeed trapped negative permittivity in a material right at the center of the vortex. And this business of negative permittivity is a very exciting, controversial topic in condensed matter, at least in polar systems. And this was one of the first measurements of directly of the existence of the negative permittivity state. And that was published. Ajay Yadav, another fantastic student from IIT Kanpur, he did all of the synthesis work. This came out a couple of years ago. And this is the final piece of that. You can see from the phase field calculations, and indeed at the center of the vortex, you have regions of negative permittivity. Okay. This is important because this could be a pathway to solve the big problem in electronics, the 60 millivolt per decade Boltzmann tyranny that people talk about. The other interesting thing, and I will show you this again in a few minutes for a sister polar texture. The other interesting thing is that if you look at these arrays of these vortices, they look like these tubes. And you know that it looks very much like a cigarette box. So if I come in with the right radiation, for example, X-rays, soft X-rays, which have a wavelength of a few nanometers, I can have diffraction from them. And indeed, when you do this experiment, you can see that there is nice diffraction. That's a specular peak, but this is the -1 and this is the +1 diffraction peak. Now, with all the synchrotron capabilities, not only can you do diffraction with soft X-rays, you can also do spectromicroscopy with that. Meaning, I can come in with right polarized or left polarized, I'm mixing my hand now, right polarized and left polarized light. And I can do an absorption spectroscopy experiment sitting at this Q value at a particular point in the diffraction space, in Q space. And if you look at it very carefully, there is a measurable difference between the blue and the red, what the X-ray folks will call circular dichroism. And therefore, this material, this array of vortices shows circular dichroism, which is antisymmetric, meaning the plus Q and minus Q are of opposite sign. Now, there are only two known mechanisms by which you can have circular dichroism. One of them is ferromagnetism, which of course our material is not a ferromagnet. But the other way is if the material is chiral. Okay, what is chirality? Here is a quick cartoon at the bottom. You can see that this is my right rotating vortex and this is my left rotating vortex. And it turns out that these vortices have an axial component as well going through the core of the vortex. And so if you now calculate the so-called chirality, this vortex array would be a right-handed vortex. Similarly, if I just simply flipped the directions of these, I could create left-handed vortices. Okay, so although the vortices are rotating left and right, they all could be right-handed or left-handed. And therefore, if you now image this as a function of spatial distribution, this is like a 3x2 millimeter sample. There are regions where the material is right-handed, and there are regions where it's left-handed. And in a few minutes, I'm going to show you that you can actually switch it back and forth between right-handed and left-handed chirality. So what have we done here? We have taken two materials, strontium titanate and lead titanate, put them together in a certain way, create these vortices. And all of a sudden, the material where neither one of the parent compounds were chiral, the net material shows chirality. where I can also manipulate the chirality with the field to go from left-handed to right-handed. Imagine this. Imagine you could take D-glucose, that stuff which gives us all diabetes and stuff. Imagine that you could take and apply an electric field and convert it into L-glucose, which the human system cannot take. How does one go about doing that? Here is a model system where you can actually use to study how to change chirality, like the organic systems do very well. How does one rotate chirality? Typically through chemistry. But here we can use fields, electric fields, to manipulate chirality. Now, this is a paper which literally got accepted a couple of weeks ago in Nature. What some of our colleagues said was, okay, I have these tubes of the vortices. What happens if I come and shake them? So the way they did it was they came in with a terahertz pulse, very short X-ray pulse, and you ping it. And it turns out that these vortices start to jiggle in unison. Okay, and that coherent mode of vibration is called a vortexon. It's just like a collective mode in some sense. These vortices are basically doing this when you shake them. And we could calculate them with phase field calculations. And it's all very consistent that you're actually getting coherent modes of these vortices. Hey, Hide, how are you? So now I'm going to show you the last piece on these vortices, and then we will go to the sister phase. Now, if you look at this picture, what I'm showing you now is calculations, time-resolved calculations of how the vortices nucleate. If you pay attention very carefully, you will see that the vortex nucleates at the interface between the strontium titanate on top and the lead titanate here. And it goes all the way from that interface right into here. And you can keep watching this back and forth, but I will summarize it for you. This is time t equals 0. At about 40 picoseconds, that vortex is completely nucleated and gone in. Okay, that's the total energy of the system as a function of time in time steps. This is about 40 picoseconds, which is the velocity of sound in the system. As you see this, the lead titanate layer gets to its maximum energy density within about a few picoseconds, which are all the dipolar interactions. But the strontium titanate actually takes a long time. And we think that's because there's an acoustic phonon that's being launched, which is important in the formation of this vortex. This work is still being resolved because we need to understand it fully. But it's telling you that with the combination of these ultra-fast X-ray probes and theory, you can start to understand the formation of these kinds of vortices. So what are the key points? Vortex lattice has pairs of dislocations. We think there is a possibility of a clusterless, Thouless like topological phase transition in that lattice. We can see antiphase boundaries. We talked about chirality of these vortices. And we talked a little bit about the negative permittivity. And the last part I showed you was the vortexons. Okay. Now, our theory colleagues again said, hey guys, you're sitting somewhere here. Why don't you change the lattice mismatch to the substrate that you use? For example, dysprosium scandate is what we use as our substrate for the vortices. But if you go to strontium titanate, they said you should see skyrmions. We said, guys, no chance. It turns out they were right. We were able to see them. These are the calculations from phase field calculations. Ab initio showed essentially the same, that if you go to strontium titanate, you should start to see these bubbles. It took us a while to get there because the experiments were very complicated. But sure enough, if you grow these superlattices on a different substrate, you could start to see these bubble-like features. Let me blow it up a little bit more. These are the polar skyrmions. They're about 5 to 6 nanometers in diameter, of the order of maybe 16 to 18 unit cells. And you can see that they're locally ordered. There is 6-fold symmetry locally, but they don't have long-range order. Again, the part of the reason is the same thing, that it doesn't like to condense very easily into the long-range ordered state. Now, in a few minutes, I'm going to show you, oh, maybe we can play some games with this. Now, one can understand these skyrmions in essentially exactly the same way as you could understand the magnetic skyrmions. So you can define a skyrmion number, which is the surface integral of this function. This is called the Pontryagin density. Okay, this is just a normalized local dipole moment. In the case of the magnetic skyrmions, it's the magnetic moment. Here it's a normalized dipole moment. Okay. And so this paper by Yoshi and Nagaosa sensei is a very nice introduction for this. Okay, our theory colleagues, this is ab initio theory, indeed verified all of this. This is the dipole distribution across one of the skyrmions. Think of a porcupine which comes out like this. Those are the arrows coming on the top. And if you look at these arrows, those are the arrows coming in from the bottom. But the one thing that we never expected, and again, this is really kind of unexpected emergent thing, is that in addition to this so-called nail component, which goes up and down like this, there is a block component. You can see that these arrows are going from right to left. And that block component turns out to be very important. It's exactly like your belt. If you're left-handed like me, I wear my belt from left to right. If you're right-handed, you do the opposite. And therefore, these objects could also be chiral. And indeed, that's what these objects look like. This, believe it or not, this looks like a Bollywood movie, but really it is from ab initio calculations. One of our students is very good at artistry. He captured this. Each one of these is a dipole moment. And you can see that the dipoles are coming out from the surface and they're going under the surface. But you could see the block component, the belt-like feature. And these are formally called Hafions, not even called a skyrmion, they're called Hafions, again, after a mathematician. Again, David Mueller and his student did a fantastic job of doing 4D STEM imaging. And that's one image of the skyrmion, the block component in plane. That's the vector mapping for the block component going counterclockwise. This is the theoretical calculation from second principles. Calculation. This is the image that you calculate. That's the vector pattern. All seems to fit very well. And this was Shujit Das, who was an amazingly smart postdoc. For some reason, cannot get a job in India. He just has done a spectacular job. Okay, now what we've been doing in the last year or so through coronavirus is looking at phase transitions in the skyrmion lattice. And it turns out that if you go to very low temperatures, these skyrmions will start to become like snakes, and we call them serpentine patterns. Or the students here, they call it the Cheetos pattern. Cheetos is that snack that American kids like to eat. That's what it looks like. But if I change the temperature, if I go to room temperature, it starts to form bubbles. Through some kind of a Rayleigh-Taylor instability, it starts to form these bubbles. And these are all phase field calculations. The other thing that happened was when they start to go to high temperature, they were starting to stretch it a little bit, these membranes, the samples. And then it started to order. And you can see that in calculations also, they start to order. I'm going to show you a better image of that. This is the actual TEM vector map, the so-called 4D STEM image. You could see that the vortices are here. These are the rotating patterns. This one is rotating counterclockwise, counterclockwise, counterclockwise. But the guy in the center is actually rotating clockwise. So you now have a vortex lattice. Of course, it's very locally ordered. We still don't know how to make it ordered in long range. The other thing that you see is that they now start to form anti-vortices. You have an anti-vortex here, here, and here. And that's really an important thing because so far we had never seen these in the dipolar systems. And so there is evidence that there is some kind of a topological phase transition that's happening. So this work David has just submitted to PNAS a month or so ago. Okay, like I showed you for the vortex structures, these skyrmions are also chiral because of that belt that I showed you. And the way you look for the chirality is exactly the same experiment. We set up a diffraction condition. This is soft X-ray diffraction. Actually, this is hard X-ray diffraction. But you go to this point in reciprocal space, and you can do an absorption spectra. This is looking at the titanium absorption spectra, which is a very characteristic four-finger pattern. Those are the T2G transitions for the L3 levels. That's the T2G for the L2. That's the EG transition for the L3, EG for the L2. And if you look at the difference between right and left circular, there is a very strong difference in absorption. And therefore, there is very strong circular dichroism, which is also anti-symmetric. So we know that the skyrmion lattice, the arrangement of skyrmions is also a chiral arrangement. It can be right-handed or left-handed. Okay, I'm going to finish up my presentation with one last topic that we should talk about. And this again has to do with what are the physical phenomena. In this case, we're going to talk about permittivity. So if you look at the structure, these are just some test structures. This is the superlattice. And when Sujit measured the dielectric permittivity, this is what he saw. The blue data is what he saw for the superlattice. He saw a permittivity of 800. We said, oh, that is too large. It cannot be possible. He measured multiple samples, etc. Always give a very large value. And very systematically, it'll change with the number of superlattice layers. Now, if you measure pure lead titanate, you should get a permittivity of the order of about 70. Okay. 50 to 70 is a good number. Similarly, if you measure pure strontium titanate, you should get a permittivity of the order of maybe 150 at room temperature. Instead, we were getting a value of about 800 in a superlattice where you had series combinations of dielectrics. And we said, oh, that's very fascinating. What happens if you apply an electric field? And it turns out that when you apply an electric field, that dielectric permittivity will change by about 75%. And by the time you hit about 1.5 megavolts per centimeter, which is about 15 volts across a 100 nanometer sample, you can bring the dielectric permittivity down to something that looks very normal. This is very reversible. In a few minutes, I'm going to tell you that this is a topological phase transition. It goes from a structure that has topology in it to something that doesn't have topology. It's a field-driven topological phase transition. On the right side, basically, I'm showing you the same data, but in this case, we have second principles, phase field data, and also X-ray scattering data, all of them superimposed. They're all basically telling you the same thing, that indeed, that when you apply a field to this fermion array, you can start to see a change in the dielectric permittivity. But the first question is, where did this enhanced permittivity come from? And for that, we can go back to theory. This is phase field calculations, field driven. As you apply an electric field, you can see these fermions start to shrink, 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 and boom, they'll go away. Okay. And then, well, let me pass on this because this is telling you the same thing as a static picture. Our ab initio colleagues told us, hey, look, when we do ab initio calculation for a single fermion, this is the susceptibility of the system. Chi is measuring the susceptibility. And they said right around the periphery of the fermion, the belt part of the fermion, the susceptibility of the system is very large. And typically when you have large susceptibility, you're thinking, okay, there's going to be a phase transition. Okay, so it's a very large susceptibility right around the periphery. Now I can go in and calculate the permittivity, which is related to the susceptibility. And actually you plot the 1 by the permittivity, because otherwise you get into goofy mathematical singularities. Okay, but if you look at the inverse of the permittivity, which is what we're looking for, right around the periphery of the fermion, which is right around here, you see that the permittivity is negative. And therefore, if I plot this, the entire structure in a macroscopic sense, I have these cylindrical fermions where the periphery of the fermion is a region of negative permittivity. And that's shown here modeled in a very classical EE kind of a perspective, series capacitors and parallel capacitors, except now you have regions of negative permittivity shown here in blue, which are forming part of the structure. That region of negative permittivity is exactly the same region of negative permittivity in the vortex structure. In the vortex that was a core, in the fermion, it is the surface of the fermion. And therefore, you can indeed go back and calculate that you can get very large effective dielectric permittivities when the periphery of the fermion has negative permittivity. So here is a second example where these objects, these quasi-particles called fermions, have negative permittivity built around them. All right, and it turns out that because of this negative permittivity, you can have very large enhancements in the dielectric permittivity all the way up to, this shows 10 gigahertz. We now have data all the way up to 100 gigahertz that it has very large dielectric permittivity. And clearly these are of interest for microwave circuits and stuff like that. The fact that you can tune the dielectric permittivity with an electric field is very valuable. And it's all arising from the negative permittivity at the periphery of the fermion. Okay, Just to complete the picture, these fermions and vortices look very different. They arise for essentially the same kind of reasons. It's a competition between elastic energy and electrostatic energy, but topologically they look very different. These look like long tubes, and these look like bubble-like structures. Also, to complete the picture between magnetic and polar fermions, if you look at the free energy functional, this is what we started the discussion. It has the exchange, the DMI, the Dalechinsky-Moria interaction, and the Landau energy. Here you have the Landau energy, the electric, elastic, and the gradient energies. There is nothing like the Dalechinsky-Moria interaction. So the physics of these things are very different. Of course, exchange interaction is very strong in magnets. Dipolar interaction is strong. Anisotropy is weak in magnets. It's strong in ferroelectrics. The spin cannot vanish to accommodate these competing interactions. The dipoles indeed can vanish. You can manipulate the magnitude of the dipoles, so on and so forth. Okay, all right. So what have we told you today? I hope you have taken away a few things. First is there's a lot of fun things in discovery science. As you do the translation, all the engineering stuff, don't forget to do fundamental science. It's very important. There's some fantastically smart people. Please do basic science. We talked about forming these topological structures. They're chiral, therefore they have optical activity. They show negative permittivity, very interesting phase transitions like the Kosterlitz-Thouless kind of phase transitions. And I showed you data on the fermions as well. And it turns out that this design process I told you about using epitaxy is not only for lead titanate and strontium titanate. There are many such examples, but that's for a different talk. Thank you very much again, Professor Bharati, for the opportunity to join you guys and give this talk. If you have questions, I'm happy to take them.
Thank you very much, Professor Ramesh. I just was impressed how many things in common appear in solid state physics, which I left long time ago.
Right.
In optics, when we have all chirality, vortices, of course. I have a question in the queue from Dr. Murugan. What's the future applications of multiferroid nanocomposite?
Oh, yes, very good question. If you remember in the beginning of my talk, Murugan, I talked about beyond Moore's law. So the other talk that I didn't give today had to do with how do I get to an attojoule logic element or a memory element. If you look at today's memory and logic, they work at picojoules, maybe 50, 100 picojoules per logic operation, CMOS. So a couple of years ago with the Intel people, we published a paper in Nature which talked about a magnetoelectric spin orbit coupled spin-based logic device, where you can use spin to do logic operations like inverters, and or operations, but you would manipulate that with electric fields. And the magnetoelectric, not just the composites, but the magnetoelectric structures would play that role. And the reason we want to go to voltages or magnetoelectrics is because energy consumption is significantly lower and you use voltages rather than currents. And so 1/2 CV squared is a measure versus I squared R in a current-based device. Did that answer your question, Murugan? I hope so.
He's mute.
He's muted. That's right. Yeah.
Anyway, I don't see any other question in the chat, but I have a question.
Yes, please.
So you mentioned about this large epsilons, and as you may imagine, as a guy working in optics, I am extremely impressed. I know you can get high epsilon for terahertz, but I immediately have a question to you. What about imaginary part? Because in many of the systems which we are dealing, this real epsilon is really large, but as soon as we start adding some materials with plasmonic properties and metals, simultaneously our negative part is very large. So just wondering what is the value and what are frequencies? Yeah. Okay.
As you can see there, yeah. So the loss is not zero. Tan delta is not zero, but it's not a very large number either.
Yeah, not so huge. Yeah.
Right. Yeah.
but it's not optical frequencies.
Not yet. That's this measurement is in the microwave frequency. Actually, we have already the data. I just didn't have the time to put it together into the talk. We have a lot of beautiful data with second harmonic optical measurements and stuff. Where we see similar effects.
That's extremely interesting because what I'm working on now is so-called metaphotonics.
Yeah.
Which requires high index dielectrics.
Yeah,
so the
exactly.
idea is to squeeze light or electromagnetic wave inside of small volume, where epsilon over n, over wavelength over n, is just actual wavelength in material, and then it starts to resonate with the size.
Yeah, so exactly. Right.
Large is extremely crucial to make wavelength structures. I see more questions. Just sorry,
Yuri, I would be very happy to talk to you separately to see if there is things that
I already make a note that I will send you email, but let's finish.
Yes, please.
Okay. Abhay Sagade.
Thank you, Professor Ramesh. Thank you so much for your.
All right. Okay. By the way, ask the students to send me the questions we can answer later.
Yes.
Okay.
Thank you.
All right.
So you have questions to read or to ask? What is the arrangement? Okay, I read what I have here. How the spin dynamics respond to temperatures which are used for applications, for example, for 10 or 60 degrees.
I see.
We ask about response to temperature.
So how about this? I think Professor Bharati is anxious to close this talk down and go to the next one. Abhay and Tushar, why don't you send me an email? We can talk about these, okay? These are not trivial questions, but I can explain to you later.
Okay. So
all right.
We are behind the original time anyway, so...
Right, exactly.
Thank you very much.
Thank you, Yuri.
For me, it was really a lot of discoveries. So
pleasure to meet you, Yuri. Thank you.
Thank you.
Thank you, Professor.
Yeah, thanks. Hide, great to see you.
Pass it to organizers,
So,
Okay, so we need the slides for next talk. Hello?
Hello, just wait.
Yes.
Okay.
Yeah. So next speaker today is also very famous scientist, Professor Hideo Hosono-san from Tokyo Institute of Technology in Japan. You see his slide and his awards. I just mentioned that because of a short time, I just announced his title, and we will go ahead because you already may be familiar with his achievements. So Hosono-san will be talking about recent progress in transparent oxide semiconductors. Please.
Okay.
Yes, Professor, you can share the slide.
You see that's my slide?
Yeah, please share. You can share.
Okay, so thank you. Thank you.
Hide, this is Ramesh. Can you share your screen? We cannot see your screen.
Really?
Yeah.
Where?
You should hit the green box and then share.
Green box?
Right in the center of your screen, at the bottom of your screen, sorry.
Bottom of the screen? Green box? No green box. Wow. Oh, this one? No. Sorry,
If you look at your screen for the Zoom, right at the bottom, there's a small green box.
Just wait.
Yeah.
Just wait. So that this one. Zoom. Okay, so the screen, it's can you see?
Not yet.
Just wait, just wait. This one.
Yep, coming up.
Oh, coming up? Okay,
Yep.
so,
Yeah, it's coming.
But it's working.
okay. Okay, thank you for kind introduction. My name is Hideo Hosono of Tokyo Tech. So the title is a little bit modified.
Don't see anything yet.
Yeah, progress and the issue of the wide gap oxide semiconductors. This is almost a review of our research
Sir,
in
your slide is not yet visible.
the past 25 years. Okay.
Sorry, we don't see the screen yet.
Okay. This view graph summarizes the highlight of my research. Okay, and so the glossy semiconductor is at top, and now you can see that the large size of the OLED TV in electrical shop. And this large size OLED TV or your iPad are driven our oxide TFT. And the second,
Sorry to Hosono Sensei. Hosono Sensei, we cannot see your slides.
Really?
No.
Yeah.
Please start again.
This not okay. Just wait. Oh, very troublesome. Yeah.
Sir, maybe you can close it and try to share again.
Just wait. So still no. Can you see that my slide?
No.
No. Wow.
Incompatibility between Indian and Japanese Zoom.
Yeah. So that me just wait. So
Professor, otherwise, can you send your slides to me? Can you email? I can share from my side.
wow. Just wait.
But that may be a big file. It may take a long time. It may not come through things and he need to post it on somewhere else.
Wow. Very difficult to.
Professor, I typed my email ID in the chat box. You can send to my email. I can share from my side.
Maybe convert to PDF. It will be smaller. Yes, we see you.
Yeah.
But that's it.
Can you see?
Not only you, but not screen.
No. Yeah. What's my computer?
It says you have started screen sharing, but the slides are not visible.
You can redo it.
Wow.
Can you stop sharing screen? Then afterwards you can try once again.
Yeah.
But I guess first you should see your screen, and then you may launch presentation. So there is something wrong from the very beginning.
Yeah.